Hello everyone. So in today's video, I'm going to derive from the starting equation at the top here a finite domain version of this impulse force formulation. So this equation at the top was derived in an earlier video in this series, and it relates the aerodynamic force F to the changing surrounding vorticity field in terms of this integral known as the impulse. That's here, this first integral, and a second integral over the body surface. Now the question we're trying to answer today is how can we express this in terms of flow data over a finite subdomain of the unbounded domain for which this was originally derived. So again, just to reiterate the assumptions that went into this equation, we had an physically unbounded flow that is incompressible. We have an impermeable body surface SB, and there is no vorticity that has escaped V infinity, the unbounded domain that we're looking at. So all of the vorticity is contained inside. But let's say we wanted to estimate force looking at the surrounding vorticity field, but we didn't have access to the data out to infinity, which is a practical concern in many cases. So we want to look at subdomain, which I will here call V1, we'll call the boundary around it S12, and I will call the remainder V2. So V infinity, as originally defined, is just going to be equal to V1 plus V2. So the first thing we can do now is split up this integral. So we can see that this is an integral that is linear in terms of vorticity. So there's no problem in simply summing up the integral over the two different domains and ascribing force components to what's happening in one domain versus the other. So if we do that, we have a force expression that's going to look, let me just back to my other style, that looks something like this. Okay, there, so we've divided up and I've color-coded those two sub-integrals of V infinity over V1 and V2. And now, of course, our challenge is going to be to express what's going on in this second integral in terms of flow data over V1 or its outer surface S12. And I should emphasize that for today, I'm just looking at the two-dimensional case. So if you recall from the more general derivation before, we'd have factors of 1 over n minus 1 on these impulse integrals if we were considering in general 2D or 3D. So we're just going to look today at 2D for simplicity. All right, and the way forward is I'm going to want to take this time derivative operator and move it inside of this second integral. But to do that, I'm first going to have to express this integral over a material volume. So let me define here V2m is going to be a material volume which happens to occupy the space V2 at the specific instant in time that we're looking at, because of course we're expressing the instantaneous force here. And the integral of impulse over the material volume, we can relate to that over the static fixed control volume using the Reynolds transport theorem. So we have here that the time rate of change of impulse in the fixed control volume is equal to the time rate of change of the impulse in the material volume minus this flux term. So we have the flux of impulse leaving the domain. And let me just add a little sketch to remind us of the distinction between material volumes and static volumes. So let me draw some arbitrary static volume, which I will call V2. And at a given instant in time, we're going to have a material volume that occupies exactly the same space. So we'll call that V2m, or rather I should call it V2m at time t0. And then at a later instant in time, we're going to be following that same matter, that same material volume, which will have moved relative to the static volume. So we'll have some slightly deformed volume and the deformation relative to the original is related to the velocity at the surface. So then we have this relationship between the static volume, the material volume, and that's related via this flux term involving velocities at the surface. So this part is review. The Reynolds transport theorem should be something you've seen before in a standard momentum analysis. Now, the reason that we're doing this is, once again, so that we can move this time derivative operator inside. So when we're looking at a material volume, we can write, so we have, so we've moved that operator inside, and now we have these material derivatives. I've used capital D dt to indicate that this is a local material derivative, and because the position x is now following material particles and not referring just to a specific point in a fixed domain, this position derivative is just velocity, and this term here we can manipulate by recourse to the vorticity transport equation. So let me quickly write out the vorticity transport equation in the normal form. I'm going to show it in full 3D form, and then we'll simplify for 2D. So here it is here, and we have the unsteady term, the convection term, the stretching and tilting term, and the diffusion term. Now recall that when we're expressing it in this way, this unsteady term is referring to the change in vorticity at a specific point. But if we combine these first two terms, we're actually getting back the material derivative. So that is the rate of change of vorticity of a fluid element that we're following. So now we can take this right half and substitute that in. Now we have an additional simplification, because in 2D, this term is going to vanish, so we're going to be left only with the diffusion term. Now, just to get our bearings again, so we don't lose track of where we are and where we're going with all of this, let me rewrite out the original equation. That is the original equation after we divided it up. And this is going to be equal to the first and, oops, didn't mean to delete that original one. So we have the first and third terms that are just coming back unchanged, and then this second term is going to become this flux term, and this integral involving u cross lambda, which is often referred to as the u cross omega, which is often referred to as the lam vector, and this term involving the diffusion of vorticity in the material volume V2. Now recall, our goal here is to express everything in terms of what's happening in V1 or on S12. So far we haven't made much progress to that, although we have this flux integral. So this boundary of V2 is going to include S12 as well as S infinity. Of course, vorticity is 0 on the outer contour S infinity. We've defined that on purpose. So that means I can actually simply replace this with S12. I do need to change the sign here. That just has to do with the convention of the direction of the normal vector. Don't worry too much about these little details. What I really want to sketch for you is how we're getting from the starting equation, how we're going to relate what's going on in V2 to what's happening in V1 and the physical processes that are going on. So speaking of the physical processes, the changing impulse in the material volume V2, we have here a convective process and a diffusive process. And let's actually color code these two processes so we don't lose track. So there they each have a distinct color. And now we note something else here. Because we're no longer taking the derivative of this integral, we can actually just get rid of this little m subscript that we'd introduce on both of these, because there's no time dependence. This is just an integral, a sum over that volume. V2m at any instant is occupying V2 by definition, so it doesn't matter anymore whether we call this a material or non-material volume. And at last we can relate these now to something going on the surface S12 by some vector identities. So the first is this one. So that lam vector integral is related to a surface integral involving a flux term here and another term involving the square of the velocity. And for time, I'm not going to prove it, but because we have all the vorticity contained inside of S infinity, even though this boundary of V2 comprises both S12 and S infinity, this integral over S infinity is going to be 0. So in our particular case, this is no longer an identity, but in our particular case, we're going to have this, and I am going to change the sign of that so that this n is facing into V2. And the second identity we need gives us this expression here, and I've moved the nu there. If I didn't say before, is the kinematic viscosity. I've treated that as constant, so we're looking at a Newtonian fluid. I've moved that outside the integral. So this is S12. And again, I'll make sure that we have n pointing outwards on S12. If you want the source for these identities, because I've given them without proof, you can consult these references, which I'll give in full either at the end of the video or in the comment or the little description below. All right, so if you're still with me so far, good job, because I'm doing this fairly fast, and this is difficult vector calculus manipulation. But now we're going to substitute all of these different things that we've done back into the equation to show what we've achieved. So I'll just scroll down here. So in this top line, we have the original equation where we divided up the impulse into what's happening in V1 and V2. And now I've color-coded this, so V2 is contributing into all of these different sub-integrals. Now the reason I've gone to the trouble of showing this whole derivation, because obviously I haven't shown every detail how it's done, and it's not strictly important for you to use this equation that you know how to derive it in detail, but to know where it comes from. So if you were to simply stumble upon this equation in a paper on vortical impulse theory, like Noca's thesis or Kang et al.'s paper that I cited above, it would not be immediately clear that all of these terms have to do with the changing impulse outside of the domain V1 that you're considering. So they sort of look, well, they just look like complicated terms. So this gives you an idea of physically what's happening, and we can even physically go a little deeper. I can reestablish the color coding I used before. So these last two surface integrals are communicating the changing impulse in V2 due to the physical processes of vortex convection and vortex diffusion, respectively. Now this term up here, this is a flux term, so this also has something to do with convection, but we could also connect this term with the first term. So now I've color-coded those together. If we combine those together by our Reynolds transport theorem that we looked at earlier, this is actually showing us the material derivative of impulse in V1. So that's another way to interpret that. So here now we have the finite domain version of the impulse formulation, and we've derived this specifically for, though we're looking at a finite domain for a physically unbounded domain, it does actually hold as well, no matter what's going on. So if you had a constricted flow outside of V1, inside of an enclosure, for example, this actually still holds. Now, I haven't proven that with the derivation I've shown, but Noca in his thesis does show that. And let me just scroll down here to that general equation. So I haven't obviously proven it here, but in 2 or 3D, To express it generally, we have these factors of 1 over n minus 1 again, where n is the dimension, 2 or 3, as we had in previous videos. And we have one extra term here that we didn't have. So recall when we introduced the vorticity transport equation, in 3 dimensions, the vorticity field is being manipulated by the processes of tilting and stretching. So this term is representing the tilting and stretching, and that effect, the effect of that on the impulse in V2. So once again, everything from here on is related to the changing impulse in V2. We could also express this in terms of what's going on in V2, or we could combine it to talk about what's going on in V1. So I think that's a good place to leave it for now. This is a good general starting point for both unbounded or non-unbounded flows. As I said, I haven't proven that, but Noca did. And I'll leave it at that for now. If you have any comments or questions, please leave them below.